The second simple gas law that we're going to learn about is called Charles' law, after the man who quantified it. So he lived back in the 1800s, and he looked at the relationship between the volume of a gas and its temperature. Bless you. And he found that the volume of a gas was directly proportional to its absolute temperature. And so Charles's law says that volume is proportional to temperature at constant pressure and amount of gas. So we can express it like this, but we usually do it like this: V1 over T1 equals V2 over T2. And very important, the temperature must always be expressed in kelvins. You can't use Celsius, you can't use Fahrenheit, it has to be kelvins. And this is why. So here's some data looking at volume versus temperature, volume on the y-axis, temperature on the x-axis. And so this is, both of these, or all three of these, are at 1 atmosphere of pressure, but the amounts of gas are different. And we see for each amount of gas, there is a linear relationship between volume and pressure, volume and temperature. What's interesting here is that if we extrapolate the lines, meaning drawing the lines past where the data actually is, we find that all of these lines intersect at a temperature of negative 273.15 degrees Celsius. Now that is the conversion relationship from Celsius to Kelvin. You have to add 273.15, and this is where it came from. So at this point, zero volume at 0 Kelvin. So that's the absolute lowest theoretical possible temperature, is where the volume of a gas would be so small that it's 0. Of course, that actually can't happen, but these all intersect here. So the reason we have to use Kelvin is because when we look at the equation for a line, if we have a non-zero intercept, then it's not just a direct proportionality anymore. So by using Kelvin, then we get, well, this is the volume is equal to the slope times the temperature plus 0. So then we have that direct relationship. So you have to use Kelvin, and negative volume is not possible. Molecular view of Charles' law: if we take a balloon from an ice water bath and put it into a boiling water bath, the balloon is going to grow, it's going to expand in volume. And if we think about what the molecules are doing, we understand that as the temperature increases, the molecules are going to move faster, right? So they are going to collide with the walls of the balloon more often and cause it to expand. So the volume increases as the temperature increases. The balloon will maintain a fairly constant pressure, and the only way for it to do that is for it to expand. So remember, Charles' law, we're looking at constant amount of gas and constant pressure. So by expanding the volume, the pressure can be the same because you spread out those increased collisions over a greater surface area. This, of course, is a picture of a hot air balloon, and I remember being fascinated by these as a child. I mean, let's think about it. If you blow up a balloon with air and tie it, does it float? No, it does in cartoons, but not in real life, right? You have to put helium in it to make it float. And if you have a hole in the balloon, all the helium comes out and it doesn't float anymore. So here we have a balloon with a giant hole in the bottom of it, and it's full of air, not helium, and yet it goes up into the air and carries people in a basket. What? It's magic. No, it's science. It's not specifically just chemistry, it's also kind of physics, but we can claim it as chemistry as well. So they've got this great big burner here, and what that does is it heats the air. What happens when you heat a gas? It expands, right? So a lot of that air is going to get pushed out the bottom. The pressure is going to be the same inside and outside. But as the gas expands, it's got fewer particles in that same volume, its density decreases. So the hot air inside the balloon is less dense than the cold air outside the balloon. And just like wood floats on water because wood is less dense than water, hot air will float in cold air. And so by controlling the amount of heat, you can get the balloon to go up and down. Now, the side-to-side business, you're just at the mercy of the wind. Could end up all kinds of places. Anybody have any questions about that? You may have also seen this happen. You can take a little, like a paper bag, and you can make a little lantern thing with a candle and get a paper bag to float up into the air, and that's pretty neat also. So let's do a problem with Charles' law. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? So we read the problem, and then we're going to highlight the numbers. That's the stuff that we're given. We've got 88.2 milliliters, 35, and 155 degrees Celsius. And then we're going to find what the question is, what they want us to find. Volume in milliliters. Now, the example for Boyle's law, we drew an ugly picture. For this one, we're not going to draw an ugly picture. I'm going to show you a different technique where we make a table to help organize this information. So this table is going to have 2 rows and basically 2 columns with headers. So as I go through this, I'm just going to collect these numbers and put them in the table. So the first number is 88.2 milliliters. So I'm going to put that right here, 88.2 milliliters. And we have 4 parameters: pressure, volume, temperature, and amount of gas. So what is this? Volume. So I'm going to label that column V. I'm going to put all the volumes in the V column. Now it says if we heat the gas from 35 to 155. This says this was the initial volume, so that would be at the first temperature. So this is the first set of conditions. So this is 35 degrees Celsius, and it goes to 155 degrees Celsius. So I'm going to call the second row 2, and I'm going to call this column T because those are temperatures. So this represents V1, this is T1, this is T2, and this is the thing that's missing. That's the volume. So I'm going to write V2 in there. Now, do we need to be worried about any of these units? Yeah. Temperature has to be in kelvins. So we need to convert these to Kelvin. So 35 plus 273.15, 308. So this is where it gets a little messy. So technically this is 308.15 Kelvin, but the last significant figure is in the ones place. And so what your book does a lot is they'll just add 273, which you generally end up getting the same answer, but it bugs me because it doesn't really follow what we're supposed to do, which is if you have extra digits, carry 2 extra digits along. When we carry those digits along, then it makes everything kind of messy, and so we're just going to call that, let's not do that. We're just going to call that 308, which is rounding it on an intermediate calculation, which you're not supposed to do, but the book does it. So, 155 plus 273.15, we're going to get 428. Now, an interesting thing happens a lot with temperatures. Our initial temperature had two significant figures, but when we're adding, we're looking at the decimal places, so it goes to the ones place. So now the number has three significant figures, and that happens. Okay, so there's all of our information. This is telling us, of course, that this is Charles' law. If it didn't have a label like that, we would look at the variables we have here. We've got volume and temperature, and we need the simple gas law that has V's and T's in it, right? So that one is V1 over T1 is equal to V2 over T2. The trouble with this equation is it has fractions in it, and people do crazy things when they rearrange it. So unless you're really good with math, or you want to come talk to me and I'll show you the short way of just flipping sides, cross-multiply this to get rid of the fractions, then rearrange it, and you're much more likely to get the correct answer. So cross-multiplication, in case you don't remember, is where you multiply the top of the one side by the bottom of the other side, and that will be equal to the bottom of the first side times the top of the second side. And it's crossing, so it's cross-multiplying. So that gives me V1 times T2 is equal to T1 times V2. It's much easier to rearrange before you stick all those numbers in there. So just rearrange it while you've got letters. We are trying to find V2, right? That's what's missing in our table. So I need to rearrange this equation so that V2 is by itself on one side. So if I divide that side by T1, then the T's will cancel out. In order to keep this an equality, I need to do the same thing to the other side. There's going to be a lot of algebra like this. So if you're not good at that, please come and talk to me and I can help you get better at it. V2 is equal to V1 times T2 over T1. I always want you to show your work. Do you have to do all of this part? No, you don't. The minimum is you need to label your numbers in some way. Some people find the table is really helpful. Other people might just say, well, this is volume 1, right? And this is volume 2, and just kind of label them right in the question. That's fine. But I do want to see the rearranged equation and the equation with the numbers and units plugged into it. Because then if you make a mistake, we can see where the mistake was, so you can learn from it and not do it again. So we're going to plug these numbers in. So volume 1, we just find it in the table, 88.2 milliliters. Always, always, always include the units. And then T2, but be careful, T2 is down here, it's 428 Kelvin. That's going to be divided by T1, which is 308 Kelvin. If we look at the units, we have Kelvin in the numerator and the denominator. They cancel out. So we get 88.2 times 428 divided by 308. How many sig figs should this answer have? 3. Because this temperature has 3. We don't just look at what was given, because sometimes those temperatures especially will change. But all of these have 3, so we should have 3 sig figs. The unit is milliliters, because that's the only thing that didn't get canceled out. And so rounding that to 3 significant figures, 123 milliliters.
Does that mean because we're rounding the Kelvin, this will almost always be 3?
The temperatures will almost always be 3.
Okay.
Yeah. Occasionally there'll be more, because if we recorded this with a more precise thermometer, like even our glass thermometers, we can estimate to the nearest tenth. So if this was 35.5 degrees Celsius, then I would say definitely you should include the 0.15 part, right? But a lot of times here, it's just to the nearest degree, because the point here is not to make your life miserable with sig figs and extra digits. The point here is, can we learn how to solve the problem? Okay. Any other questions? 123. Okay, this is a conceptual connection problem, meaning we shouldn't have to really do any math. Not that there isn't math involved, but we don't need to calculate. So the pressure exerted on a sample of a fixed amount of gas is doubled at constant pressure, and then the temperature of the gas in kelvins is doubled at constant pressure. What is the final volume of the gas? These problems can be very hard to think about. Personally, I'd rather they just give me numbers and ask me to calculate it, right? So let's think about this. So the pressure, we have a fixed amount of gas, so N isn't changing. The pressure is going to double at constant temperature. So if I double the pressure, what does that do to the volume? Does it get bigger or smaller? It gets smaller by the same factor. So that means the volume is going to be divided by 2, right? So now we've got half the volume. And then it says, now the temperature of that gas in kelvins is doubled at constant pressure. When I double the temperature, does it get bigger or smaller? It's bigger. Let's think about balloons, right? I don't know if this has ever happened to you. I've had 6 kids, and so we've been to a lot of birthday parties. And you bring home some helium balloons, and you leave them in the car, and it's winter. You come out the next morning, and they're all sitting on the floor, and you're like, oh. But you bring them inside, and they perk right up and start floating again. It's the temperature difference. When they're cold, they shrink. When they're warm, they expand, right? So, and that's partly why if you put balloons on your mailbox or something to help people find your party, a lot of times they'll pop. And it's always the dark ones that pop first. You know why? The dark ones absorb more energy from the sun and heat up faster. And if you blew them up or put helium in them so they were really nice and firm, it expands too much and they pop. And so you'll notice the dark balloons are all popped and the lighter colored balloons are fine. Chemistry and birthday parties. Okay, so where were we? We had our gas was half the initial volume, and now we're doubling the temperature. So increasing the temperature makes it bigger. And if we're doubling the temperature, what does it do to the volume? It also doubles. So changing the pressure cut it in half, and then changing the temperature doubled it again. So we're back where we started from. So the final volume is the same as the initial volume. Any questions? Where's the train? The train has a question. The train never hangs around to get the answer, though. They just keep going. A third simple gas law. This one's called Avogadro's law. So, Amadeo Avogadro, the same guy of Avogadro's number. It's hard to imagine there'd be multiple Avogadros. He was the first one who formally stated the relationship between the volume of a gas and the amount of a gas in moles. Now, he wasn't talking about moles because moles hadn't really been created yet, but he was looking at the number of gas particles, not the mass of the gas, but how many particles there are. And that's actually what eventually led to us creating the mole as a unit and it being a certain number of molecules. So the volume of a gas is proportional to the number of gas molecules. And of course, this is where we hold temperature and pressure constant. And so this is often stated as V1 over N1 is equal to V2 over N2. So of course, we count the gas molecules in moles instead of individual molecules. And what's really, really interesting here is that equal volumes of gases contain equal numbers of molecules. It doesn't matter what the gas is. That's not true of solids or liquids. If you have equal volumes of solids, they are almost certainly not going to have the same number of particles, right? Because one is more dense than the other. But gases aren't like that. So if you do an experiment here looking at volume and amount of gas, so here's, that looks like, I don't know, maybe 0.6 or 0.7 moles of gas. I'm 0.07. No, I'm sorry. Never mind. It's just that. Sidetracked here. As we increase the amount of gas in the container, the volume increases. So that makes sense, right? You puff one breath of air into a balloon and it expands. You put more air, it gets bigger, right? You put more gas in, it gets bigger. If we extrapolate this past the data to the end, we get the prediction that 0 moles of gas would occupy 0 volume. Well, that makes sense. So this, kind of combining those three, which action causes the volume of a gas sample to increase? Got decreasing the pressure, decreasing the temperature, decreasing the number of moles of gas, or none of the above. A, decreasing the pressure. So if we decrease the pressure on the gas, that allows it to expand and get bigger. Okay? If we decrease the temperature, that causes it to shrink up. Right? If you decrease the moles of gas, if you take some gas out, it's going to get smaller. Any questions? So here's an Avogadro's law problem. A chemical reaction occurring in a cylinder equipped with a movable piston, we find a lot of these in gas law problems, produces 0.621 moles of a gaseous product. If the cylinder contained 0.12 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? Assume constant pressure and temperature. Well, let's make a table and collect this information. So find the numbers. We have 0.621 moles of gas. We have a volume of 2.18, and we have 0.12 moles of gas. And then the question is, what is its volume? So the first number I come to is 0.621 moles. Is that P, V, N, or T? That's N. N is the amount of gas in moles. So that's moles. So it says this much, and here's the other one. 0.120 moles. That's also N. And then we have a volume of 2.18 liters. Now, it's important to connect that volume with the correct amount of moles. So we do have to look at some words here. So this is producing this much. So that's at the end, right? And here it contained this much before, so that's first, right? And an initial pressure or initial volume, so that's also first. So on here, I might want to call my second row, row 1, because that is the before situation. So I'm going to label this 1 and this 2. And if that bothers you and you want to write your table the other way around, feel free. But the volume of 2.18 liters belongs with the 0.12 moles. Everybody okay with that? So that is volume. Yes?
Does it, do these equations matter if it's liters, milliliters, and?
No, they don't actually. So in the simple gas laws, as long as the units of the quantities are the same, so here the volume, if we're starting with liters, we're going to end up with liters. As long as the volumes are the same, the units are the same, they'll work out. The exception is temperature, has to be Kelvin, but the others can be anything. So I'm looking for this missing box here, which is in the V column and in the row that I labeled 2. So Avogadro's law started out to be something else. V1 over N1 is equal to V2 over N2. And I definitely do not expect you to remember the names of these laws, okay? This one also has fractions in it. Cross multiply, get rid of the fractions. So V1 times N2 is equal to N1 times V2. And then I'm looking for V2. So I need to divide by N1, so those guys cancel out, and do the same thing over here. And again, if that part gives you trouble, please come and ask me, and we will figure it out and make it make sense to you. So there's my equation. Now I'm going to plug the numbers and their units in. So I'm supposed to have volume 1. There's volume 1 is 2.18 liters. And N2 is 0.621 moles. And that's going to be divided by N1, 0.120 moles. And then I look at the units, and moles are going to cancel out. Occasionally, they're not very nice, and they might give you an amount in grams and make you convert it to moles. But these first ones, they're a little kinder. So 2.18 times 0.621 divided by 0.12. 11.2815 is what my calculator says. That would be liters. How many sig figs? 3. So I should report this as 11.3 liters. Any questions? Okay, here's another one. This is a little different. A scale model of a blimp rises when it is filled with helium to a volume of 55 cubic decimeters. That's an odd volume unit. When 1.1 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. So this is the kind of question that could show up on an exam where we only did things like the straight volume moles thing, right? This one's different now. It's throwing something else in there. It's requiring you to think about it, think critically, and to figure it out. And there will always be at least one question like that on an exam in Chem 1A. This is one that might be helpful to have ugly pictures. So we've got a blimp that's floating. So maybe this is our blimp that's floating. And we have a blimp that's not floating. And it's all collapsed on the floor. So we're filling this blimp with helium, and when it floats, it has this volume. So here, as it's floating, we say the volume is 55.0 cubic decimeters. Down here, the blimp is not completely empty. It has 1.1 mole of helium in it. So that would be N, 1.10 moles of helium. And the volume down here, with that little bit of gas in it, is 26.2 cubic decimeters. I should have highlighted these things. Any questions on how I attach those numbers to the pictures or anything? You read a question like this, and it's probably not going to be obvious what you need to do. But that's how life is, right? You come across all kinds of things. You're like, I don't know what to do. So you just go home? No, you figure it out, right? So here it's like, well, we can do this. We're going to pull the numbers out. We're going to maybe draw ourselves a picture and label things to help us see what's going on, right? Well, I've got 2 volumes and a mole. Could I find out how many moles are in the floating blimp? Yeah. So maybe let's try doing that. So I'm going to call this N1, N1 and V1. And we'll call this one V2, because that comes later, right, after you fill it up. And then I'm going to try to figure out what N2 is. N2 is not going to be the answer to the problem, but it's a step in the right direction. So V1 over N1 equals V2 for N2. Here we're solving for something in the bottom, so this is where it's really, really important not to screw up your algebra. Again, let's cross multiply. And then we want to get N2 by itself. So N2 is going to equal N1 times V2 over V1. So N1, 1.10 moles. V2, 55.0 cubic decimeters. And V1, 26.2 cubic decimeters. Like, those are weird units. Yeah, they are. But look, they cancel out. We don't have to deal with them. Gone. 1.1 times 55 divided by 26.2. So 2.3092 moles. How many sig figs? 3. So that's how many moles we have up here. So let's put that into the picture. 2.3092 moles. Okay, so we calculated something. Yay, us. We haven't answered the question yet. So this is saying how many grams of helium do you have to add to this flat balloon, flat blimp, to get it to float? What can we calculate right now? Can we calculate how many moles we need to add? Yeah, because this is the number of moles we need for it to float. And if we subtract how many moles of gas were in there to start with, that's how many moles we need to add. Can we convert moles to grams? Sure, we can almost do that in our sleep now, right? So if I have 2.3092 moles and I started with 1.10 moles, that is 1.2092 moles. That's the number of moles added to make it float. How do I convert that to grams? I see eyes looking at the periodic table. That's right. We need the molar mass. Be careful with the units. Yesterday when it did this problem, I did it wrong. I caught it because the units showed me I was doing it wrong, but we want moles on the bottom, and we want grams on the top, because that's what we're trying to get to. Going from moles to grams. Then we go to the periodic table, and we see that helium has a molar mass of 4.003, and our moles are going to cancel out. And so this should still have 3 sig figs. So we need to add 4.84 grams of helium to get it to float. Any questions?